Welcome back to Analog Electronic Circuits. This is the 9th lecture, and today hopefully we will be working on the source degenerated amplifier. Now, in the last several lectures, over the last 8 lectures, we have understood the MOSFET, how it behaves, and then we have looked at the 3 basic circuits: common source, common drain and common gate. Right. We have examined these 3 basic amplifier circuits. The common source amplifier is the most generally the most popular one, and it has reasonably high voltage gain. It has infinite input impedance, but it has a large output impedance. Then comes the common gate circuit. The common gate circuit also has very high gain, voltage gain, right, but the common source amplifier had negative voltage gain. This had the common gate amplifier has positive voltage gain, but then it has a low input impedance and a high output impedance. Okay. Low because the input was at the source, and looking into the source the input impedance is low. Then the third structure we looked at was the common drain circuit, and in the common drain circuit the gain, the voltage gain is approximately equal to close to 1. Okay, that was the voltage gain. Actually, it was less than 1. We calculated some body effect and so on and so forth, right, you recollect? Yes. And the input impedance of the common drain circuit was infinite, very large. The output impedance was very low because the output was at the source. Remember, the source is the low impedance node, the drain is a high impedance node, the gate is infinite impedance. Okay. So, if you take the output from the source, the output impedance is low. If you apply the input into the source, then the input impedance is low. Okay. Now, and then, so all of this we studied, and then I said that there are 2 important structures that you have to analyze for impedance. One important structure was this. So, looking into the drain when the gate is terminated to ground, when the source is terminated through RS to ground, right, looking into the drain, what is the impedance? This was one question, and a second question which looked exactly similar was this. Okay, looking into the source, what is the impedance when the gate is terminated to ground and the drain has RD to ground, right. These are all in the small signal. Okay. And then we did some calculations. We had actually solved this second one, not the first one, right, and this calculation was a little lengthy because it involved some sort of KCL, KVL, let us just quickly do it. So, for example, if I assume that the current going this way is I, when I have applied a voltage V, okay, I have applied a voltage V, let us assume that the current going in is I, and now let us compute the overall voltage. So, let us do a KVL loop like this. Okay. So, V is equal to, this current is also I, right. So, the drop across the resistor is I times R D, and then there is the drop across the source drain of the MOSFET. Okay. So, I do not know what is the source drop across the source drain of the MOSFET, I need to figure out. Fine. Sorry, this is not V D S, this is V S to D. All right. Now, what is inside the MOSFET? You have got this is the structure. Okay. There is RDS, there is GM times VGS and GMB times VBS. And now, inside this the source is at voltage V, the gate is at ground. So, GM VGS is really minus V. So, let us correct this. Okay. And likewise VBS, the body is at ground, the source is at V. So, GMB VBS is nothing but minus GMB times V. So, I am going to correct it to point upwards with GMB times V. Okay. So, those are the two currents in those two elements. Total current over here was I, which means that the remaining current through this RDS is I minus GM times GMV minus GMBV. So, the current through RDS is nothing but I minus all right. This is the current through RDS, and the voltage drop across RDS is therefore this times RDS, and that is going to be VSD. So, this is the KVL. Okay. Now, put all the V's together. So, I have put all the V's together and put all the I's together. And that will give me V by I, that is the input impedance, is equal to all right. Now, this result happens to be important enough that you need to memorize it for this course. Alright, this result is important enough that you need to memorize it. You also have to memorize the context, that is what was the experiment that was done that gave this answer, that also you have to memorize. Do not just memorize the answer, because if there is no context you can't do it. So, this result is important enough that for this course you need this result. Okay. And likewise, the second one, this I asked you to try in your free time, but nevertheless we are going to do it right now. So, this is looking into the drain, what is the impedance. So, let us try that. Once again we can do a KVL, we can assume that this current is I. So, this current is I, this current is I, which means that the drop across RS is I times RS, right. I have applied a voltage V, current is I. So, V is equal to drain to source voltage plus I times RS. Okay. And now all I need to figure out is what is that drain to source voltage. For that, think of what is inside the MOSFET. This is what is there. That is what is there inside the MOSFET. So, the drain is at a voltage V, source is at I times RS, gate is at ground. So, what is GM times VGS? Source is I times RS, gate is at ground. So, I am going to correct GM times VGS to point upwards, and the value will be GM times RS times I, that is the current pointing upwards. And likewise, this is GMB times VBS, body is at ground, source is at I times RS, which means I am going to correct this to point upwards at, and the value is now going to be GMB times RS times I. Fine. I was the total current through the MOSFET. Okay. So, what is the current through the resistor then? What is this current? This current is nothing but I plus I times GMRS plus I times GMBRS. That is this the green current coming through RDS, and therefore, the voltage drop across RDS is this current times RDS, and that is VDS. Okay. This you plug in over here. Now, let us take a look, let us rewrite that top equation. So, V is equal to VDS, which happens to be this complicated expression, which is nothing but I times RDS plus GMRS RDS plus GMB RS RDS, that is VDS, and then I times RS. okay, and then simplify to find out Z D, which is nothing but V by I, and that is R d s plus R s Okay, so, this is the result, and once again this result is so important that you need to memorize this result to ace this course, to understand this course also, you know, because I am going to invoke this, right, from time to time I am going to invoke this. So, if you want to understand this course, all right, even for understanding sake, because every time we are not going to compute, right, we need to pull things out of our memory from time to time. So, therefore, I am recommending, not recommending, I am letting you know that if you want to understand the remaining part of this course, then it is vital that you memorize this expression and memorize this expression, expression 1 and expression 2. Okay. Impedance looking into the source is so much, impedance looking into the drain is so much, right. These two need to be absolutely memorized, because they are vital for you to understand the course. Okay. Am I clear? Memorize these two results right away. Looking into the drain, the impedance is going to be high, it is going to be R d s plus R s plus the gain of the MOSFET G m plus G m b times R d s, that is the intrinsic gain of the MOSFET times R s, what is on the bottom. Okay. So, once again let us look at it, I am trying to help you memorize this. Okay. Let us look at it. You are looking in to the drain of the MOSFET, you see that on the source of the MOSFET there is R s. So, the net impedance is this source impedance plus the intrinsic gain of the MOSFET times the source impedance plus R d s. Source impedance plus the intrinsic gain of the MOSFET times the source impedance plus R d s. Okay. Looking into the drain of the MOSFET, you see a high impedance, the impedance multiplies up. Okay. How much does it multiply? It multiplies up by a factor of the intrinsic gain of the MOSFET, right. This is a large number, I need you to understand this. Okay. While understanding, memorize. Next one, looking into the source, what do you see? So, I am looking into the source of the MOSFET, the drain is terminated with R d. Now, naturally looking into the source, I am going to see a low impedance, right, but there is an impedance which is R d and there is also R d s, and it looks like R d s is in series with R d. So, it is R d plus R d s, and because it is low, this whole thing is divided by the intrinsic gain of the MOSFET, 1 plus the intrinsic gain of the MOSFET. Okay. I am trying to help you memorize these two results, because they are so important, we need them right away, we need them in every lecture we are going to invoke these two formulae. Okay. They are important. Is it understood? You are going to memorize these? Yes, you need to memorize these to come to the next lecture. All right. Now, with this background, what we have seen so far is looking into the drain, impedance is very high, it multiplies by the intrinsic gain of the MOSFET. looking into the source, the impedance is very low, it divides by the intrinsic gain of the MOSFET. Okay, this is what we have seen so far. Our next circuit is going to be something that more or less looks like the common source amplifier. But remember, when we studied the common source amplifier, first when we did the biasing, there was an R1 over here, there is an R2 over here, right, and then there was RS and there was RD. This is what we had done during the biasing of the MOSFET. And then what did we do? We had the capacitors to couple the signals, right. So, we had an input capacitor to couple the signal in, we had an output capacitor to take the signal out. Okay, in the small signal equivalent picture, incremental picture, these capacitors are short circuits. Then we said that RS does not appear in the small signal picture at all, right, it was not there because we wanted to make a common source circuit. So, we wanted to have the source connected to ground. So, therefore, we had placed a capacitor over here across RS. Over here, right, and then we analyze the circuit. This was our common source amplifier. Now, the question is, what if this last one, this capacitor was not there at all? What would have happened? How will you solve this question? Okay. So, the way we solve our questions is by using a Norton equivalent model. So, first of all, let us redraw. That is all in the redrawing, right. The green input and output capacitors are short circuits. The red biasing resistors come in parallel with the input voltage source and they make no difference to the circuit. All that remains are the MOSFET, RD and RS, and instead of VDD, instead of the power supply voltage, you will have 0 volts over there in the small signal incremental picture. Okay, this is the story so far. Now, the question is, what is the voltage gain? How are we going to find this? We are going to evaluate the voltage gain of this circuit using the Norton equivalent method. How do we use the Norton equivalent method? We are first going to do the short circuit test. We are going to measure the short circuit current and then we are going to measure the output impedance of the circuit. Okay. So, for now let us assume that RD is the load. RD is the load, it is going to be in parallel with the load anyway. If there is some other load RL, then RD and RL are in shunt with each other. So, you will write it as RD parallel RL. So, nothing will change over there. Let us assume RD is outside as part of the load, and let us just look at the bare minimum, that is this portion. All right. Now, first experiment, I am going to apply V in over here. I am going to connect the output through a short circuit to ground, and the question is going to be, what is this short circuit current? All right, this is going to be one experiment that I am going to do. The second experiment that I am going to do is, I am going to measure the output impedance, and to measure the output impedance you are going to null all the inputs, which means you are going to connect the gate to ground. This we have just done, right. What is this output impedance? We have just done it. You remember RDS plus RS plus GM plus GMB times RDS times RS. GM plus GMB times RDS is the intrinsic gain of the MOSFET times RS plus RS plus RDS. Okay. That is the impedance. One experiment done already. I am not even expanding the MOSFET, I do not need to know what is inside anymore. Okay. I am just using that expression, earlier expression. Okay. Now, the other experiment has to be done. I need to find out what is IN. Now, this is something that you have already done, haven't you? Isn't this the common drain circuit? Isn't it? Isn't it the common drain circuit? The drain is connected to power supply over here. Drain is connected to power supply. You have got some resistor on the source. This is indeed the common drain circuit, and we have already studied this. So, what did we do in that case? We found out the value of voltage over here. This was some output voltage that we had figured out, okay, in that case, and we had, remember, we had figured out that the gain, the voltage gain was less than 1. You want to do it once again? Okay. So, if you want to do that, let us forget this experiment, right. Let us assume this is connected to ground. We eventually want to find out IN, but let us for now just find out V out. Okay. Now, to find out V out, you are again going to use the Norton equivalent method. What does the Norton equivalent method? What is it? It has two parts, find out the short circuit current and find out the output impedance. So, I look at this node, what is the output impedance? I can look down, I see RS, and when I look up, I look into the source of the MOSFET. RD is 0 ohms to ground, right. So, my formula, this was formula number 2, I am referring to this formula, looking into the source of the MOSFET. RD is 0 ohms, right. So, the impedance is RD plus RDS, RDS plus RD is 0 divided by 1 plus GM plus GMB times RDS. This was the impedance looking up, okay, and looking down I have got R s, which means that the net impedance is the parallel combination of this and R s. So, this times R s divided by something like this. This was the impedance over there, right. That is done. I am trying to find out this voltage. Okay. Now, the next thing is what was the short circuit current. So, if I connect this to ground, what would be the current through it? If I connect this node to ground, drain is also ground, source is ground. So, inside the MOSFET there is GM, GMB, RDS. The current through RDS is nothing but 0 because both terminals are grounded. The current through GM is V in times GM, okay. And the current through GMB, body is at ground, source is ground, is 0. Okay. So, the current, the short circuit current is nothing but GM times V in. Okay. So, my short circuit current is GM times V in. The impedance at that node is this complicated expression, which means that the voltage over here is nothing but GM times V in times this. Okay. So, this is the voltage. You do not remember a complicated expression, is that it? That is the question. You do not remember the complicated expression, correct. You do not remember the complicated expression because we had worked with conductances at that time, not with resistances. You will see that if you work with conductances, things become a lot easier, right, because these are in parallel. Okay. So, for example, two resistors in parallel, right, you have to do R1 R2 divided by R1 plus R2. If you had done two conductors in parallel instead of resistors, then you would have just done G1 plus G2, and in that case the expression would be the same GMV in over here, but instead of a multiply it would be a divide by GS, and that is in parallel with this conductance, right. This conductance is 1 by of what I have written here. So, it is 1 by RDS plus GM plus GMB RDS by RDS. You see, it is a lot simpler, right, if you work with conductances. So, that was the voltage over there. Okay. So, if that is the voltage, then what is this current? That voltage divided by R s, right, and that is the same as this current I n. So, I n is nothing but this V out, this voltage over here divided by R s or multiplied by G s, whichever way you want to look at it. So, my final expression for I n is G m times G s divided by G s plus G d s plus G m plus G m b. That is my expression for I n, and my expression for the output impedance is so much. Okay. Would you like to convert this to G's, to conductances? It would be a bad idea generally to convert this to conductances, because these are all in series, right. but you can do it. Okay. RDS is 1 by GDS, RS is 1 by GS, all right. So, this output impedance is nothing but so much. Okay. So, this is the output impedance. This is the reason why I did that actually. Okay. Note this numerator and this denominator are the same, they are the same. Okay. Very good. So, I have the output impedance, over here, and I have the short circuit current over there. So, what is the model? The model for the circuit, remember I have taken out RD, RD is not there, the drain resistance is gone, right. So, the model for the circuit is this. So, these are the two quantities that you have computed. Why is the current pointing that way? Because the current is pointing this way when you measured it, right. So, when you replace this by a short circuit, the current is going to be consistent with your measurement, that is why. This is important what I just said. This you have to maintain consistency in direction, right. This current, when you did this short circuit experiment, the current pointed in this fashion. Over here, if you had a short circuit instead of RD, the current would go in the same direction. So, what is the voltage over here? I n times minus I n times Z d parallel with R d. Or minus I n divided by this output conductance plus G d. And then what is I n? We had it from here. That is I n, and what is Y d? This is Z d. Okay. So, Y d is 1 by this. And the drain conductance. All right. And then of course, these two are the same, which means that this entire thing is going to simplify Okay. Is it fine so far? All right. Now, what we are going to do now is we are going to first multiply numerator and denominator by R s, and then we are going to multiply numerator and denominator by R d, okay, just because I want to. So, numerator and denominator, let us multiply both by R s times R d. So, what happens over here when I multiply numerator by R s R d, the G s goes away and R d stays. Denominator, I am going to multiply by R s R d. So, this becomes R d and this becomes R s, all right, and this is where I stop doing work and start interpreting things. Okay. What is the interpretation? So, first of all, G m is supposed to be, if you have done a good job with the transistor, then G m is hopefully large. So, if G m is large, all right, especially compared to G d s, especially compared to G d s, G m is large. So, let us throw out the terms with G d s, let us just focus on the G m term. This again there is a G d s, although it is G d s times R d, I do not know the relationship between R d and R s, but let us assume that R d and R s are relatively similar resistors. Okay. They might not be 1 k and 1 k, maybe they are 1 k and 5 k, relatively similar, but G d s is much smaller than G m. This is my first assumption. In a very good transistor, the ideal transistor, G d s is 0. So, if G d s is 0 for example, then this entire term goes away, this goes away, right, and the denominator is dominated by G m, which means let us forget G m b and let us say that G m is much larger than G s. After all, G s is in your own hands. Okay. So, let us make G m the dominating factor over here, in which case the entire denominator is going to become G m times R s. The numerator is only G m times R d, thrown out. So, what do you get? This is approximately equal to G m times R d divided by G m times R s and that is a very nice result. Okay. The gain of the amplifier is just minus R d by R s. Actually, it is lower than that, but that is kind of an approximation to what the gain of the amplifier is going to be. Let us look at it in a different way. This was the circuit. Okay. So, if you say that you have got a source follower, common drain circuit, the drain resistance did not really matter, right, at that time, in which case the voltage over here is more or less equal to V in. That means, this current is V in by R s, this current is V in by R s. So, the drop across R d is V in by R s times R d, and therefore, the output voltage is minus V in times R d by R s. Okay. And where was the approximation over here? The approximation was to make an estimate, initial guess, or rather an estimate, not a guess, an educated estimate that the voltage at the source is more or less equal to V in, right. It is actually less, it is less substantially, it is less by actually a factor of so much, which kind of reflects in this picture. Okay. So, if you ignore this term totally, if you say that GDS is nothing, even then you will be left over with this portion. Okay. Is this okay? So, this is a neat little circuit, right. You throw out that capacitor and then what do you see? You see that you have got a gain which is related to the resistor values only, not no longer to the device parameters. So, your gain is now minus R d by R s, right. If I choose some resistor ratio, even when temperature changes, the resistor ratio is going to be maintained and therefore, the gain is going to be maintained more or less a constant, and this is something very nice. All right. However, you are not going to get large gains. Why not? Why won't, can R d be equal to 100 times R s? No, R d cannot be equal to 100 times R s, because then you have to do the full work, right. If R d is 100 times R s, then remember we had thrown out this term over here, right. There was an R d in the denominator. This is going to come back into play and then your gain is no longer going to be minus R d by R s, it is going to be some a number much smaller. So, R d can't be arbitrarily large. Fine. So, this is called the source degenerated amplifier, what we had up front. This is the source degenerated amplifier. There is a resistance at the source. So, the source is degenerated. Now, I want to have a few words, some important, but rather abstract words, and these are going to be some abstract comments. Try when I have the following discussion, try not to be overly rigid, okay. Be a little flexible, give me some leeway, right, and then maybe you will have a better time following this course. Okay. So, what do I want to say? Suppose I want to make a battery. If you want to make a battery, right, you invariably end up with some source resistance, and that source resistance appears in series with the battery, with the voltage source. So, if you try to make a voltage source, you will never end up making an ideal voltage source, you will always have some series resistance. Okay. To make a very good voltage source, this series resistance has to be made lower and lower. Fine. How low this series resistance is gives you a quality of how good this voltage source is. So, a very good voltage source will have a very low series resistance. Fine. Is this comment understood? The reason why I said do not be too rigid is because this low, this value low, what is low? This is all subjective. I mean, what I call low, you might call it too high. Okay. In electronics, we call 0.1 ohms as low, but you go to power engineering and you say I have got a wire with 0.1 ohms, they are going to laugh at you. That is not a wire at all. Okay. So, this high and low, this is all very subjective. Let it be, let it remain subjective. For now, just go along with the flow, right, just listen to what I have to say. So, what I have to say is as follows: if I want to make a voltage source, I need a low series resistance, or in other words, if I make a circuit that has a low output impedance, then it behaves like a voltage source. So, the backwards thing is also applicable. So, if I have let us say a box and I measure the Thevenin equivalent or Norton equivalent impedance of this box, right, and if this output impedance is low, then that means this box behaves like a voltage source. Is this okay? All right. Next, a current source. Suppose you try to make a current source, you will never really make an ideal current source, you will always end up with some resistance in parallel with it. Okay. Now, this is not in series, this is in parallel. If this is current source in series with a resistance, is a current source. Voltage source in parallel with a resistance is a voltage source. Current source in series with a resistance is a current source. The non ideality is when the resistance appears in parallel. Okay. If this resistance were to be infinite, then the current source would have been an ideal current source. So, therefore, if you are trying to make a current source, then you need a very high shunt resistance. Okay. In other words, if you have made a box and you find the Thevenin or Norton, they are the same, right. The Thevenin equivalent impedance is the same as the Norton equivalent impedance. If you find out this output impedance of this box and find out that it is high, again low and high, these are all relative terms and subjective. Okay. So, keep it that way, let us keep it subjective, let us keep it relative. When the output impedance is high, I am going to call this box a current source. Is this okay? Is this understood? Very good. So, low output impedance, it is a voltage source, high output impedance, it is going to be a current source. Then suppose I have a circuit which has an input impedance. Okay, this is my circuit, and then you know it has some control mechanism, maybe it is a control voltage, control current, whatever it is. Okay. So, it could be a controlled voltage source or a controlled current source. Now, suppose this impedance is very high. If this impedance is very high, then whatever is driving this node, this from outside, let us change the color. Maybe it is a voltage source is driving this node, or maybe it is a current source that is driving the node, it does not matter. Whatever is driving the node, this if it is a voltage source driving the node and this is a high impedance, then this voltage is the same as this voltage. So, you know the voltage over here, the voltage over here does not change because of the impedance over here, right. So, we call this voltage control. Okay. So, a voltage controlled source will have a high input impedance. Okay. Likewise, if there were a current source over here and you wanted current control, then that current source would have some shunt resistance. And this is the input of your box. Okay, the current source has some shunt resistance. Now, if you want the current over here to be equal to the current source value, then this impedance should be high or low? It should be low, because if it is low, then this entire current is going to go this way. Okay. So, a current controlled source has a low input impedance, and now you combine. So, you have got a voltage controlled voltage source, voltage controlled current source, current controlled voltage source, and current controlled current source. These are the 4 controlled sources that you have learnt, right. Voltage controlled voltage source, voltage controlled means that the input impedance has to be high. Voltage control means the input impedance has to be high. Current control means the input impedance is low. And then if it is a voltage source, then the output impedance has to be low. If it is a current source, then the output impedance has to be high. All right. So, for example, if you have a common gate circuit, a common gate amplifier, okay, it has an input impedance that is low because it is at the source, and the output impedance is high because it is at the drain. What is it then? All right, input impedance is low, output impedance is high. So, we should not look at the voltage gain at all, because it is a current controlled current source. Okay. Then if it is a common drain circuit, the input impedance is very high, the output impedance is very low. All right. If it is a common source circuit, then the input impedance is high, the output impedance is high. And so on and so forth. Okay, I do not have an example right now of current controlled voltage source. Right now, I do not have it. Maybe so if you want to make a current controlled voltage source, you place a current controlled current source which has a high output impedance, and then you are kind of stuck. Then you can put a voltage controlled voltage source at the back end, okay, which has a low output impedance. Okay, voltage VCVS has an infinite input impedance. So, this high output impedance will not matter. Okay. So, you could do something like that. But anyway, I just want to give you this was a relative picture of how, what is a current source, what is a voltage source. It is a relative matter, it is totally subjective whether a source is going to behave like a voltage source or a current source. It is relative, right. It all depends on the impedance of the source. Okay, thank you very much. See you in the next class.